Nassim Taleb proposed a heuristic for categorizing modern occupations. Divide them based on how closely an individual's income is chained to their time. In a non-scalable occupation, you are paid by the hour or by the specific task. Your income is strictly bounded by the physical limit of hours in a day. Even the most efficient dentist can only see so many patients before the clinic closes. Scalable occupations decouple income from time entirely. An author writes a book once, and that single effort can yield one sale or 100 million sales. This creates a winner-take-all environment, where a tiny fraction of participants captures the vast majority of the rewards. Mathematically, these two job types map to completely different probability density functions. The income of non-scalable professions should cluster tightly around an average, creating a thin-tailed Gaussian distribution, or a bell curve. Scalable professions should generate a heavy-tailed Pareto distribution. In a heavy-tailed distribution, the average is meaningless. The system's entire mathematical profile is dictated by the extreme outliers at the very top. This heuristic makes intuitive sense. To prove it actually governs human income, economists need to test it against real-world microdata. A team of researchers applied this exact test to a 2017 Brazilian dataset containing the individual earnings of workers across 12 specific occupations. The objective was strict: isolate the upper tail of the income distribution for each profession and calculate its Pareto exponent, represented by the Greek letter alpha. The Pareto exponent acts as a direct measure of tail thickness. A smaller alpha value indicates a heavier tail, which translates to massive, winner-take-all income inequality. When the researchers processed the data through standard statistical optimization models, the results contradicted the theory entirely. The algorithm concluded that the single most extreme heavy-tailed income distribution, the profession with the highest degree of winner-take-all inequality, belonged to motorcycle messengers. Professional soccer players, by contrast, scored as highly egalitarian. Either a globally recognized economic framework is backwards, or the standard algorithms data scientists use to measure income inequality possess a massive mathematical blind spot. To find the error, we must look at how a Pareto Type 1 model is built. The first step is to plot the complementary cumulative distribution function, also known as the survivor function, which simply isolates the population earning greater than a specific amount. This chart is a Zipf plot. It graphs the logarithm of that survivor function against the logarithm of total earnings. Notice how the data points begin to align into a straight line interval on the far right side of the plot. The negative slope of this exact straight line is the Pareto exponent, our alpha. To calculate that slope, you first have to pick a starting point on the x-axis. This threshold, called XM, defines the exact dollar amount where top earnings officially begin and the heavy tail starts. This threshold selection is the structural vulnerability of the entire model. Start measuring the tail in the wrong place, and your inequality metric collapses. The researchers initially relied on standard optimization algorithms. They programmed the model to maximize the R-squared statistic, effectively letting the software find the mathematically optimal cutoff threshold for each individual occupation.
This table shows the initial results of that optimized run, ranking the 12 occupations by their calculated alpha. Motorcycle messenger sits at the absolute top, with a remarkably low alpha of 1.07, indicating an incredibly heavy tail. Down at the bottom is the footballer, with an alpha of 7.32, suggesting the extreme earnings of professional athletes are tightly clustered and highly egalitarian. The software executed its instructions perfectly. By blindly trusting a best-fit algorithm, it output a mathematically pristine, economically impossible conclusion. Two distinct variables caused the algorithm to fail. First, the dataset is right-censored. The absolute highest earning outliers simply aren't in the database. For Brazilian footballers, the true top earners, megastars playing in European markets, do not appear in domestic labor records. The extreme right tail of the footballer distribution is literally truncated. Second, the algorithm was allowed to pick different starting thresholds for different jobs. The optimal cutoffs it chose varied wildly, initiating the tail anywhere from the top 9% of earners down to the top 0.2%. These Zipf plots show how the algorithm reacted. For messengers, it isolated a single courier earning 80,000 rial, fitting a massive heavy tail to that one point, forced the model to compare incompatible scaling regimes. It measured a fraction of a percent for one job and nearly 10% for another. To strip away the algorithmic distortion, the researchers threw out the optimal R-squared cutoffs entirely. They established a single, uniform rule: calculate the OLS estimates strictly for data above the median earnings, applying this exact threshold across every occupation simultaneously. This chart shows the dataset re-ranked using a uniform median threshold. The scalable jobs, footballer, musician, and actor, shoot to the top, producing the smallest alpha values and heaviest tails. The non-scalable jobs, bank clerks, dentists, and motorcycle messengers, fall straight to the bottom. Forcing a standardized threshold proved that the strange initial results were a statistical illusion. When you look at the same segment of the population across the board, the true distributional architecture of the economy appears. The microdata ultimately confirms the hypothesis. Scalable occupations decouple from time, allowing participants at the top to capture wildly disproportionate rewards. Conversely, when measured correctly, wage labor remains structurally bounded. You cannot work 100 million hours in a single day, and your income distribution reflects that physical limit. This reveals a critical vulnerability in applied data science. Optimizing strictly for the best statistical fit, without understanding the physical limitations of your subjects, will reliably generate false realities. This risk compounds when dealing with right-censored datasets. If the most extreme outliers are missing from your records, an automated model will attempt to build a tail out of local noise. Rigorous mathematics only yield truth when the parameters are standardized across cohorts. The human context of the data dictates how the algorithm must be constrained.